up is Troy Howe. Troy is from right up the street. He is the son of Stephen Howe, who some of you probably have run into at various times. And Howe Industries is their company up in Tempe or somewhere in the Phoenix area. And he's going to talk about his pulse plasma rocket. Take it away.
Thank you. I'm here to talk about the pulse plasma rocket, which was a project that we did for the NASA NIAC program. And our idea here was to try to get an extremely high performance nuclear-based propulsion system, kind of building on some previous work in pulse thermonuclear systems. So if you look back at the history of these pulse nuclear propulsion systems, kind of the first one was the Orion concept back in the 1970s, where the idea was basically to drop a nuclear bomb out the back of your spaceship and let that explosion propel you forward with extremely high performance capabilities. There were some technological obstacles that kind of prevented this from seeing reality, and as well as some political obstacles. So the concept of putting a spacecraft into Earth orbit that was equipped with thousands of nuclear weapons would probably receive some complaints from other countries. And so it never really materialized, but it was an interesting concept nonetheless. Following on those footsteps, Dr. Rob O'Brien from NASA Marshall, or Dr. Rob Adams from NASA Marshall, was able to come up with this idea for a electromotively driven concept, where instead of using high explosives to implode your device, you would use huge current of electricity to implode it, and then you didn't have the issues of deployable nuclear systems. It was all there on the spacecraft. And then our concept is just a continuation kind of this idea, where instead of using high explosives or electromotive forces, we actually just use the neutronics. So we have a nuclear-driven nuclear system for the pulse plasma rocket. Next slide, please. The basic idea here is that we've got a low-enriched uranium barrel and a low-enriched uranium projectile. And when those two are put together, they form a supercritical system and start producing a lot of power, with most of that power focused in the projectile. And the original concept would be driven just from these two pieces being forced together, but we've upgraded that to give us a little bit more control that I'll go into a little bit later. We did want to use the high assay low enriched uranium, or HALEU, because it does add a lot of safety and cost alleviations. So the whole thing is primarily low enriched, moderated, very available, very usable materials, and still get you the very high performance and low mass. Next slide, please. So the thing that we added on that is kind of a big leap forward in our concept is these control drums, where normally you would have one side being a neutron reflector and another side being a neutron absorber. And as they rotate in or out, then you kind of raise or lower your criticality of your system. Since we've got 6 control drums in our design, we explored the possibility of rotating them at different speeds. And if you have a series of different sine waves, you can add them together to make a Fourier series approximation of other functions. And in our case, what we wanted to do was have a near constant criticality. So when the projectile is passing through the barrel, it's generating heat at a predictable rate, but then right at the end, when it starts to vaporize and turn into a plasma and needs to ionize, we really need to cover a lot of ground really fast there. And so ideally, we would have a delta function where it's constant and then a very sharp spike at a certain point. And since we've got the ability to add these sine waves together from the rotating drums, we can actually simulate that just with our own control system. So down in the lower right, you can kind of see the approximation that we've been able to generate with our spinning drum system, where it varies a little bit around a certain value, and then right at 1 second really peaks. And that's when we drive all the energy into our projectile and kind of explode that out the back. Next slide, please. So based on this design, we were able to design a rocket that could reach 5,000 second specific impulse, 100,000 newtons of thrust, take over 18,000 kilograms of payload to Mars, and do a 106-day round trip to Mars and back. So very fast, high performance. The animation on the right is just kind of showing the projectile going through the barrel, coming towards the end when that criticality flashes, and it pushes you away on your way to Mars or wherever you want to go. Let that guy finish up. And next slide, please. So the topics that we investigated for this project were really the neutronics. It got kind of complicated with the criticality and our control system and the dynamic system. And then the thermal concerns were definitely playing with fire here, dropping an explosive device out the back of the rocket. The nozzle is really integral in catching that. So we've got a plasma full of ions that we need to prevent from hitting the spacecraft. And then just the general operation on how much power does it take to work? How do you reclaim it? What's its capabilities and stuff? Next slide. So the neutronics is complicated in the fact that we need to maintain a positive criticality above 1 so that we can generate power, but we also have to keep it kind of under control so that it doesn't run away and explode ahead of time. And so we were able to show that we can achieve criticality and have a critical assembly with our rocket, but we also had to then take into account where all that power is being deposited. What's our power profile look like? And we wanted it all to be in that projectile. And so the projectile is designed to be what we call a good reactor. It's low enriched uranium fuel. It's got moderator in it. The neutrons that are formed from fission moderate and then create new fissions in that projectile. And then the barrel around it is what we were calling a bad reactor. It's low enriched uranium, no moderator or very limited moderator out there. So it takes a very large mass for it to really contribute to the criticality. Now, it seems like it's a bad idea to have a bad reactor in your nuclear system, but it actually helps us really focus all of that power generation in a specific spot. And so the chart in the lower right shows for different moderators in that projectile, what is our ratio of power in the projectile versus the power in the barrel. And it's all pretty good based on these designs, but really once you put water in there, it's such a good moderator that it just jumps up to 25-to-1 ratio. And so for every degree temperature that we raise in the barrel, we get 25 of it in the projectile, which comes out really useful. Next slide. The other thing that's very interesting with this system is that since we're modeling a projectile passing through a barrel, it's not really a regular nuclear system, which normally you have a critical assembly that you analyze as a single state of being, but ours is passing through. And so according to the projectile, since it's having all of these fission events take place, it doesn't necessarily know that it's moving. They're on a much faster schedule than the projectile is passing through the barrel, but the barrel is seeing this wave of neutrons pass through it. And so once the projectile gets to the middle or the end, the front of the barrel is not really participating as much as it was before. And so it's an interesting concept and makes it a little bit more complicated to understand the population of your neutrons as they start growing exponentially because you're supercritical. Some of them are left behind in the barrel and some of them are still in the projectile. And so it's an interesting approach. And we had to do it just by splitting it up into different steps and modeling it as a solid state or a steady state at each step. But there's definitely a lot of work to be done on this type of dynamic analysis. And you can also see there at the end, we ended up adding a sleeve of highly enriched uranium onto the barrel. So we're not transporting projectiles made of it, but it really does help in that peak of criticality at the end to get our projectile to flash into a plasma. Next slide. Our thermal analysis showed that we can definitely deposit more heat in the barrel and keep the barrel cool enough so that it doesn't melt. And there's a couple of key aspects that contribute to that. One of them being that traveling wave, just like with the neutronics, the heat also travels down the barrel. So it's not all focused on a specific section. The front of the barrel and the back of the barrel are heated at different times. The barrel, being a poor reactor, has a significantly higher mass than the projectile. And since we're firing at a rate of 1 hertz, we can really flash this and cool the barrel. And we've got a lot of time kind of to extract that energy that's been deposited. And so that helps us keep our barrel from melting. There was a significant issue with photonic heating. So once we turn it into a plasma and eject it out the back, it glows really, really brightly. And those photons will hit a very shallow skin depth in the spacecraft and heat up that small amount of mass that it's interacting with to really high temperatures, and it'll actually ablate tungsten walls. And so one approach is to make your wall really, really thin and cool it. But our approach was actually to make that penetration depth a lot longer. So we used a semi-transparent sapphire shield that, instead of stopping those photons in a few microns, would stop them over 10 centimeters. And now, instead of heating up grams of material with all that energy, we were heating up kilograms, and we could address it in a similar fashion to the barrel. We could cool it. We could really take advantage of some of those pulsed aspects in that duty cycle. And so it turns out that, based on our analysis, we can heat up slowly until we melt. And then right as it turns into a gas, we flash it and we get up to that electron volt temperature range very quickly before that hot gas hits the edges of the walls. Next slide, please. The magnetic nozzle is very important for making sure that once we've generated this plasma, it doesn't come back and run into us in any way. And so there's strong electric currents traveling through a coil at the back of the rocket. And those magnetic field lines trap any charged particles that come in contact with them. And so there was a couple options of doing a solenoidal coil or an axial coil. How much power was needed? What kind of pressures do we deal with there? And so we were able to devise a nozzle that was able to contain the plasma. We chose to go with the axial coil, so the copper goes up and down along the axis instead of wrapping around, and that helps us direct the plasma as it explodes a little bit better, but both ways were valid. And then you can just kind of see in the lower right, at different time steps, how that plasma expands and how it's directed in a certain direction with the help of these coils. Next slide. So just during regular operation, we need to accelerate that projectile up to about 1.6 kilometers per second. So we use a coil gun to launch that in really, really fast. The fission process raises it up to 1 EV temperatures, and we get a good ratio of power generated versus power that it takes to actually start the thing. The average power that it takes to fire these projectiles once per second is about 5 megawatts. And then we're able to recuperate a little over 200 megawatts from the coolant. So the barrel that needs to be cooled so it doesn't melt is basically a big heat exchanger, and we extract heat from there with our working fluid, and then we use that to convert it into power to power the rest of the system. The nice part about that is that now that we have the drums and we're not dependent on the projectile to drive the system supercritical, once you get to your destination, you can also use this as a bimodal electric power system. You can just turn on your reactor and kind of have plenty of electric power for whatever you need. Next slide, please. So since this is Interstellar Conference, I did want to kind of discuss about what interstellar options we've got. Our ISP and our thrust are good, but they're not good enough to get to another star. We have some options of improving that performance. We could probably get to hotter temperatures with more developments, but even then, it's just not enough. You know, we need antimatter or solar sails or something, you know, big. But we could potentially do a a kick stage. If you need to leave the solar system and you need to get out there fast, we can supply something like 51 kilometers per second delta V budget, and that was for 18-ton payload. So if you're a lot smaller, we could get you up to speed to take that first leg, or possibly a generation ship. At this point, it would be a lot of generations, but as we continue to develop it and get those temperatures up and get that ISP up past 5,000 seconds, it's an option. I don't know what the other options for generation ships are. So if anyone has any thoughts or questions on those concepts, I would love to hear it. I think that's all I had. Is that the last slide? Great. So happy to take any questions you have.
Troy, Stephen, by the way. Quick question. What is the regulatory environment for this going to look like in space?
Well, it's going to be difficult. So we're probably going to have to rely on some more traditional nuclear thermal, nuclear electric systems to kind of break that barrier of getting nuclear technologies into space. And then hopefully once we can recognize the importance of this very high performance, it will outweigh the concerns about having kind of an open cycle nuclear system up there. The nice part is you can't drop your propellant as nuclear weapons. So that's a increase over the Orion concept. Most of the ejecta that you use will leave the Earth's sphere of influence, and any charged particles will be atomized and captured in the atmosphere. So from a safety standpoint, we don't have to really worry about contaminating anything, but there's probably going to be quite a few hurdles on getting this actually up and running in the future.
Troy, thanks very much. I appreciate it, and we'll see you in person in Montreal next time.